Yeah, so I hope Oleg convinced you that sterile neutrino is a very interesting dark matter candidate, which is a part of a wider picture of the new MSM. So it's probably an element of the new standard model. And I would like to describe how, to what extent is it constrained now and what can we expect in the future. So we start probably with a few words about the possibility of direct detection. So as particle physicists, of course, we would like to detect a particle, right? It is very challenging for sterile neutrino dark matter, but it is possible in principle. There are several ways to do it. And one way is to study in details the spectrum of electrons emitted in beta decay and try to find a kink in this spectrum. Theoretically, this idea could work, but in reality, even the largest experiment, which is HEPHY, will not have enough sensitivity to come close to the parameter space, which is interesting from astrophysical and cosmological point of view. To go there, you need an improvement in sensitivity by many orders of magnitude. And people in HEPHY are thinking about it. And also an example of how this could work is given by the concept of Ptolemy experiment. It's a concept yet because, you know, experiment does not exist, and even how it will look like is not fixed completely. But this experiment has completely different experimental principle as compared to HEPHY. And also the aim is to increase the number of beta decays, increase this statistics very significantly. And formally, if you look at the numbers claimed in the papers about this experiment, this would give a possibility to have the amazing signal to noise ratio at the level of 10 to the minus 10 and smaller, which would be relevant for the part of the parameter space of sterile neutrino relevant for cosmology and astrophysics. However, this is just a statistical sensitivity. When you are talking about such very rare events and very small signals, of course, the main thing is to take into account all possible systematic effects, both instrumental, related to, for example, energy resolution of the experiment, and also physical effects, like, for example, condensed matter effects that can take place inside this experiment. And we are going to publish a paper soon about some of those effects. So it's not clear whether, how far one could go with this idea, but I'm quite optimistic because people are very smart, and typically, if there is a reasonable goal, sooner or later we are finding ways to achieve it. So I don't think that there is a no-go theorem here. But in any case, these prospects for direct detection is definitely something for future, for relatively remote future. And so far, the best way to constrain the properties of sterile neutrino dark matter is still to use cosmology and astrophysics. The first bound comes from the fact that this particle is a fermion. Fermions cannot be compressed arbitrarily to arbitrarily large phase space densities. And this was realized very early in 1979 by Lyman-alpha, who excluded in this way usual standard model neutrino as a dark matter candidate and produced a model-independent bound for any fermionic dark matter particle to be heavier than 3,400 electron volts. This bound can be made maybe an order of magnitude stronger if you use concrete model and you assume certain initial distribution function, which would come from one of those production mechanisms that Oleg described in his talk. So then you could have probably a bound close to, I mean, somewhere between 1 or 2 keV. But in any case, the particles that you are talking about are somewhere in the keV mass range. And this means, together with this production mechanisms that Oleg was talking about, that that sterile neutrino dark matter is warm. So these particles are produced relativistic and cool down later. So for longest, most recent part of the evolution of the universe, they behave as usual cold dark matter. However, at the very early period, they were streaming out while they were still relativistic. They were streaming out of over densities, homogenizing matter distribution at small scales, and removing primordial density perturbation. Sorry. And in this way, introducing a cutoff in the power spectrum or in the matter power spectrum. And so one way to constrain sterile neutrino is to constrain warm dark matter in a model-independent way, because many particles could be warm dark matter, not only sterile neutrino, and then apply those constraints to these particular models of sterile neutrino. Another important property is that sterile keV mass sterile neutrino has a subdominant. It's something like 200 times slower than the main decay channel, but radiative decay, which is tube body, and keV dark matter decays into ordinary neutrino and a photon. And from practical point of view, the energy of this photon is more or less equal to the 1/2 of the mass of dark matter. So you expect a monochromatic decay line. And this is decaying and not annihilating dark matter, meaning that the signal will scale as an integral of the density of dark matter along line of sight, which in turn means that you can expect comparable signals from many, many, many directions on the sky. You are not confined to dark matter, or to the galactic center, or some very strong peaks in dark matter density distribution. You expect comparable signal from many sources, so you can efficiently use it to constrain. And again, you constrain decaying dark matter model independently, and then you apply it to concrete models of sterile neutrino dark matter. So let's start with the warm dark matter case. So as I said, the signal here is a cutoff in power spectrum, and the more historically, a bit more traditional way to see it was to apply it to small scale dark matter distributions at low redshifts, most of all in the Milky Way, Andromeda, local universe. This is something that was extensively described yesterday by Carlos Frank, so I will not spend too much time on it. The main effect here is that you expect not to see all this enormous amount of very small clumps of dark matters that you predict is in CDM. However, as Carlos explained yesterday very well, it's very difficult to see those in any ways because they are most likely completely dark without gas and stars. And so we cannot expect too much from here. Many people try to use this data in the opposite direction, not to challenge cold dark matter, but to say we do see certain amount of satellites in the Milky Way, so maybe this can be used to constrain warm dark matter because we don't want to remove too many of them because of free streaming. In reality, it appears that for realistic dark matter, for realistic sterile neutrino dark matter, the scatter between different halos, I mean, the scatter in a number of satellites, for example, inside CE, I mean, inside warm dark matter, is larger than the difference between the two models. So absorbing only one halo, which is the Milky Way, with this substructure, you cannot say too much, especially taking into account that you see only visible satellites, as Carlos explained. So the way to go here would be to learn how to really detect the subhalos that are completely dark. And this is possible in several ways. And one promising way is to use strong gravitational lensing. So these beautiful pictures of, for example, Einstein ring can be a bit disrupted by if a subhalo is there in the lens. And modern astronomy, especially radio astronomy, but also future data from optical astronomy, is expected to give so detailed pictures of these lenses with so many pixels in each image, and each pixels bring information, that you could really see this disruption. And if you do not see them, then you could convince yourself that they probably do not exist. Of course, this is very difficult because if you see substructure, okay, that's good. You only have to convince yourself that this is not a foreground effect. If you do not see it, you have to convince everyone that this is that indeed it does not exist. It's not that the sensitivity of your approach is not as good as you expected. So people are doing a lot of work with mock data and simulations, and currently the detection limit is somewhere around the masses of classical dwarf galaxies, like 10 to the 9 solar masses, but a lot of progress is expected here, both observational in terms of data and if you want theoretically in terms of analysis and proofs that we are not missing anything in the next 5-10 years. So we can expect a lot of progress here. Another way to probe dark matter distribution at small scales is to study the property of intergalactic medium rather than collapsed halos. And this is the most powerful tool available right now here is Lyman-alpha forest. When you take a faraway quasar, which is supposed to have featureless spectrum, and then you see many absorption lines, which are all coming from the same Lyman-alpha absorption of neutral hydrogen, but at different redshifts. And you study how this absorption is distributed over redshifts along each line of sight, and then you put this all together to build a power spectrum. And what you can say here, you can check whether this power spectrum is kind of scale invariant, like in cold dark matter, or it has a cutoff feature, like what you expect in warm dark matter. And here, the smallest scales that you can probe with certain instruments are defined by the resolving power of this instrument. And the error bars on each point in the power spectrum are defined by the number of objects. how many directions of the sky you could average. And as usual, we have tens of thousands of spectra with a relatively low resolution and tens of spectra with very high resolution. So there is a little conflict. I mean, not conflict, but trade-off here. And in this low resolution data coming mainly from SDSS and we see with very small error bars this smooth, nice CDM-like power spectra, but at relatively large scale, small wave vectors. And we could use this to put a constraint. But once we go to high resolution spectra, at many redshifts in all this data, we do see the cutoff in the power spectrum. And this is not a very small effect. It's not a tiny precision cosmology. This is a big effect that you can see by eye. And this is exactly what you would expect from warm dark matter. Does this mean that you detected warm dark matter? Of course, unfortunately, no, because as usual, there are other effects that could produce the same result. And there are basically three main effects. If the gas at the redshift of observation is very hot, then the absorption lines become Doppler wide, and this removes small scale correlations from the observations, and this will result in the cutoff. To explain the data, the temperature at redshift 5 should be as high as 16,000 kelvins or larger. This is not completely excluded, but very difficult. Another effect is different. Gas started to be heated much earlier than redshift 5, at least somewhat earlier. And immediately this caused pressure in the gas. And the gas started to be removed from the smallest dark matter structures. But this process takes some time. So for gas to move away from dark matter. And you expect that in this case, the cutoff in the power spectrum will depend not only on the thermal state of the gas at redshift of observation, but also all previous thermal history. And also you expect that this cutoff will depend, its shape will depend on redshift. And of course, the third option is that dark matter is warm and there are no small substructures in dark matter, and therefore you see this cutoff. So unfortunately, the history of gas before redshift 5 is not known. There are many models here. You see the family of possible thermal histories, and you see that there is a big variety of those histories. And this all comes from poor knowledge, both theoretically and experimentally, of how reionization went. So if we take one scenario, which you see here on the plot to the left, when reionization started relatively late and went sharply, in this case, the data that are already available are not consistent with CDM. The pressure effects don't have enough time to remove the gas from small structure, and you do need warm dark matter to explain the data, to explain the observed cutoff. This is an example of how this can work. However, to really make definitive conclusions, either to exclude cold dark matter or to strongly constrain warm dark matter, we need to know more. And the data are expected to come soon. So we expect to have many more spectra at with poor resolution at larger scales, and also more data with higher resolution, and also we expect to have more and more information about the cosmic reionization epoch. And on simulation side, the progress is enormous, and this theoretical uncertainty, at least within CDM, will be smaller and smaller. So we can expect very significant progress here in the next 5 or maybe 10 years. Let's come to another property of sterile neutrino, which is decaying. The search for decaying dark matter in X-rays, which corresponds to keV mass, the first papers were written in 2000, 2001, suggesting that this is possible. And then starting from 2005, when the new MSM boosted the motivation, a lot of efforts was done, and the sensitivity was improved by several orders of magnitude. But now the most probably famous part of this story is the so-called 3.5 keV line, which was discovered independently by 2 groups in XMM and Chandra data, in Andromeda, Perseus, and also stacked data from many clusters of galaxies. And then many detections were happened after. I will briefly summarize the current situation with this. So, of course, first of all, people try to explain this line with some a little bit exotic atomic line. Atomic in the sense that it required very unusual abundance of certain chemical element, very different from solar or from what we see everywhere. This was excluded by Hitomi spectrometer, which looked at the same position on the sky where XMM have seen a strong line, and Hitomi, which had very, very good spectral resolution, resolved all atomic lines which were seen by XMM and expected, resolved with very high quality, but didn't see any sign of this line. This would be possible only in 2 cases. One, if this is systematic, or if this line is not a narrow line, if it is a wide line or a complex of lines. And then in this case, superb spectral resolution of Hitomi would not win against huge statistics of XMM. So this is not a single atomic line. This is either a complex of lines that is possible but requires quite complicated astrophysical scenarios, or it is a wide line as you would expect in cluster of galaxy from dark matter, because dark matter is not confined to one place, it's holistic. So the width of the line is defined by the velocity dispersion of the whole cluster. After that time, we detected this line in the very long, very large data set of the Milky Way, which is not only Milky Way center now, but goes as far as 45 degrees of center. And the line is detected with very high significance and in many spatial regions. And if you fit all this data with any reasonable dark matter profile of the Milky Way, relating the flux in different spatial bins according to this dark matter density profile, you get 7 sigma detection for several possible dark matter density profiles. If you just look how the line changes with distance of center and compare it with what astrophysical lines detected in the same data set, how they behave, you see that the difference is apparent, is quite significant. So it is not an astrophysical line. It's either some kind of systematics which persists for, which you can see in 4 different experiments in different observations, different objects, or this is something interesting. But the final answer to this question will be given only when we will have really spectroscopic X-ray data, which will resolve this line, its width, its position. We'll see whether it's one line or several, compare the redshift of Andromeda and Perseus, let's say. So we will have a lot of information about the line. We will compare the widths, because it should be order of magnitude different in cluster and in a galaxy. So if this line will be detected by the next X-ray spectrometer, which is X-RISM, or its first name was Hitomi 2 instead of Hitomi that exploded. We expect it to start data taking in 1 year or a little bit more if everything is fine. So this will give the definite answer what all this is about. And then, of course, if the line is confirmed in 2028, a big mission of European Space Agency that will have both huge collecting area, angular resolution, and spectral resolution, Athena will start the era of dark matter astronomy, because it will be able to trace dark matter emission from many, many directions on the sky. If this whole story will not be closed in a couple of years by X-RISM. Well, let's hope not. So this is the current status of this hint for decaying dark matter. And yeah, so here are my conclusions. I think it's just 30 minutes as I was supposed to finish. So you can see my conclusions here, and please feel free to ask questions.